Hello, I'm Jake Seifert. I'm a PhD student in mechanical engineering at Penn State University, working with my advisor, Professor Pangborn. I'm happy to present work completed with our collaborators at the University of Texas, Dallas on discrete reachability analysis with bounded error sets. This work was jointly submitted to ACC and L-CSS and is published in the latter. Consider a class of discrete time linear time varying dynamics, where feasible inputs and initial conditions are given by the sets denoted X0 and U sub k. The kth reachable set is the set of states that the dynamics can achieve from a feasible initial condition with a feasible input trajectory. Reachable sets can be calculated recursively using standard linear transformation and Minkowski sum operations. Reachable sets are often used in verification problems to ensure constraint satisfaction of safety-critical systems under disturbance, input, and parameter uncertainties. Our goal is to find over-approximations of reachable sets with efficient computations, simple representations, and quantified errors. Here is a numerical example using the exact recursion to find the first 200 reachable sets. For better visual, I shift the center of the input every 50 steps to change the equilibrium. In this case, I am using zonotopes and memory complexity grows linearly, which is quite good compared to exponential growth of polytopes using half-space and vertex representations. Still, complexity grows unbounded with time, which will lead to memory and computational limitations. For verification, over-approximation of a reachable set is often satisfactory to verify constraint satisfaction. On this slide, I present a method in which successive interval Hull approximations result in bounding the number of generators. Unfortunately, this can lead to large, potentially exponentially growing over-approximation error, often referred to as the wrapping effect. The interval Hull method leverages sequences to make interval Hull approximations of reachable sets that are tight, meaning that no smaller interval Hull exists that would contain the reachable sets. The wrapping effect is avoided, but at the cost of assuming time-invariant dynamics and input set generators. This table compares qualities of various reachability algorithms in each column, including the exact recursion and interval Hull methods previously discussed. Cascade reduction is another successive over-approximation method. It is valid for time-varying dynamics and is tunable, although explicit error bounds are not provided and error is bounded by an unknown exponential function. The proposed method, Drawbees, seeks to address time-varying dynamics while providing explicit error bounds. Furthermore, approximation error and set complexity will be shown to be tunable, allowing the user to control the trade-off between error and set complexity. Our proposed method leverages an over-approximation operator that has two outputs. In addition to the over-approximation, the operator returns an additional set that bounds the over-approximation error and satisfies the containment condition. An example shows the set Z approximated by its interval Hull Z bar. An approximation error set pi is also produced, such that the Minkowski sum of Z and pi contains Z bar. Any over-approximation method may be used, so long as an approximation error set is also produced to meet the containment condition. In a couple of slides, we will show an example approximation operator used for zonotopes. The discrete reachability analysis with bounded error sets, or Drawbees algorithm, takes over approximations of the reachable set at each time step, and adds the additional approximation error to an existing approximation error set. The updated error set is also approximated. In this fashion, both the reachable set approximations and error sets have bounded complexity. Lines 5 and 6 then propagate the reachable set and error through the linear dynamics. The main result of the paper is given in Theorem 1. The algorithm produces a reachable set over approximation and error sets that satisfy the containment condition given in equation 10. For small error sets, the over-approximation error will also be small. These explicit error sets give insight into approximation decisions and also give insight into verification, such as the potential to rule out false positives. To give a better sense of the algorithm, we give form to the approximation operators and demonstrate the benefits of the algorithm using a periodic partial boxing approximation implementation for zonotopes. Zonotopes are a centrally symmetric polytope, defined by a generator matrix and a center. Zonotopes are the linear mapping of a unit hypercube by the generator matrix and shifted by the center. The generator matrix can be partitioned, and by the properties of zonotopes, the original zonotope can be represented as the Minkowski sum of these two zonotopes. An over-approximation of Z can then be generated by over-approximating the first of these zonotopes with an interval Hull using the boxing operator. The containment condition that follows is easy to prove by splitting Z into the two zonotopes as shown previously. By comparison to the approximation operator previously defined, the partitioned zonotope that was over-approximated is a valid approximation error set. Instead of taking approximations at every step, partial boxing approximations are made periodically and are defined by the tuning parameters setting the period between approximations and which generators are left exact. When coupled with additional assumptions, the periodic partial boxing approximation scheme can achieve even more powerful results. By assuming stable linear time invariant dynamics, that the A matrix is non-singular, and that the system is controllable by U, it is possible to pre-compute error sets. The general Drawby's algorithm can be adjusted as error sets no longer are required to be computed online. By pre-computing error sets for various values of the tuning parameters, and because of the direct relationship the tuning parameters have on reach set complexity, it is possible to tune omega 1 and beta 1 to achieve a desired complexity in error. For example, the values of omega 1 and beta 1 equaling 10 will give a maximum error of around 0.06. Increasing either omega 1 or beta 1 results in lower error for slightly different reasons. Increasing omega 1 allows for more time between approximations for error to decay. Increasing beta 1 will prevent newer and larger generators from being approximated, thus over-approximating a smaller partition set will result in less increase of error during each approximation. Shown within the paper is the same numerical example presented earlier, but without shifting the input center. The example shows the exact reach set and compares Drawby's to existing over-approximation methods. Cascade reduction is shown for two values of its tuning parameter, and time steps are chosen to follow one cycle of the periodic partial boxing implementation. The exact reach set is tightly over-approximated by the interval Hall method using only two generators, but there is error at the corners. Cascade reduction error appears stable, but its relationship between its tuning parameter and the error is not clear or explicitly bounded until measured. Drawby's error appears small at the 90th time step, and the explicit error set is also small. At the 91st time step, an approximation is made, and the measured error and error bounds both grow while the complexity is decreased. Over the next 9 time steps, there are no approximations made, and due to the stability of the dynamics, the measured error and explicit error bounds shrink while the complexity grows linearly. Results show that exact computation times appear to grow quadratically, while all approximation methods appear linear due to their bounded complexity. For the example tuning parameters chosen, Drawby's is faster than the existing methods, including the interval Hall method, which is already known to be very computationally efficient. Although set complexity is higher, which increases the time to perform linear transformations, computation time is reduced overall because interval Hall approximations are only performed every 10th time step. In summary, the Drawby's algorithm provides both over-approximations of reachable sets while also providing explicit error sets. A periodic partial boxing implementation was developed for zonotopes, and under additional assumptions, error sets can be pre-computed, and the Drawby's algorithm can be specialized. A numerical example demonstrated improved accuracy and computation time when compared to existing methods, and showed that the error complexity trade-off can be tuned. This tunability, as well as the explicit error sets, provide a user with tools important for reachability analysis and verification problems. We appreciate your time and attention, and would be happy to answer any questions that you may have. Contact information is provided for the corresponding author, Professor Pangborn. Thank you.